Hello, and welcome to part 1 of our lesson on section 12.10, Taylor and Maclaurin series. In this lesson, we'll look at how to form a Taylor series, and we'll derive Maclaurin series representations for some common functions, including e to the x, sine of x, cosine of x, and inverse tangent of x. Here's the general format of a power series centered at A. When we apply the ratio test, the interval of convergence is the solution to an absolute value inequality, stating that the absolute value of x minus A is less than some constant r. Now I'll find an expression for those coefficients. Substituting A for all the x's, I find that f of A is equal to the constant c sub 0. Now I'll take the derivative of both sides, and if I substitute A for all the x's again, I find that the first derivative at A is equal to the constant c sub 1. Taking the second derivative and substituting A for x, the second derivative at A is equal to 2 factorial times the constant c sub 2. Continuing this process a couple more times reveals that the third derivative of f at A is equal to 3 factorial times c sub 3, and the fourth derivative at A is 4 factorial times the constant c sub 4. Take a look at the pattern between all of these derivatives of the function f at x equals a. They all follow a pattern in which the nth derivative is equal to n factorial times the constant c sub n. Solving this equation for the constant c sub n shows that the constant equals the nth derivative at a divided by n factorial. So the Taylor series for function f centered at a is found by the sum of terms formed by the nth derivative of f at a over n factorial times x minus a to the nth power. We define the 0th derivative to be f of a, and the value of 0 factorial is defined as 1. Expanding the series, you can see that the first few terms are f of a plus f prime of a over 1 factorial times x minus a to the first, plus the second derivative of f at a over 2 factorial times x minus a to the second, plus the third derivative of f at a over 3 factorial times x minus a to the third power, and so on. A Taylor series is a specific type of power series in which we now have a formula for those coefficients. A Maclaurin series is a specific Taylor series in which the value of a is 0. So the terms would be f of 0 plus f prime of 0 over 1 factorial times x to the first, plus f double prime of 0 over 2 factorial times x squared, plus the third derivative at 0 over 3 factorial times x to the third, and so on. In this example, I'll use the formula to derive the Maclaurin series for the function f of x equals e to the x. First, I'll calculate the first few derivatives. Then I'll calculate the value of each derivative at a equals 0, since this is a Maclaurin series. I usually keep finding derivatives until I can establish enough of a pattern to help me write a general formula for the nth term. Here, since all of the derivatives are the same, it doesn't take that long to establish a pattern. So the n equals 0 term is equal to f of 0. The n equals 1 term is f prime at 0 over 1 factorial times x to the first power. The n equals 2 term is f double prime at 0 over 2 factorial times x squared, and so on. So the Maclaurin series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial with general term x to the n over n factorial. This is one of several Maclaurin series that you'll need to commit to memory for the AP exam in May. Here's a complete list of the Maclaurin series you should memorize. List can also be found on page 803 in your textbook. You've already seen the Maclaurin series for 1 over 1 minus x. Remember that it comes from the sum of the geometric series with first term 1 and common ratio x. We just derived the Maclaurin series for e to the x in the previous example. You'll derive the series for sine, cosine, and inverse tangent in homework and classwork problems over the next few days. Press pause and take a few minutes to observe some patterns in the terms of each series, since you'll eventually need to remember them. I'll ask you about these patterns in class. This concludes part 1 of our lesson on section 12.10, Taylor and Maclaurin series.